Welcome to Plus Scale. So today we are discussing. So far we were discussing the different aspects of stereochemistry. Today we will be discussing a topic which is known as asymmetric synthesis. Asymmetric synthesis. Now you should know that any symmetric system will lead to symmetric products. Symmetric reactants will lead to symmetric products. If you want a chiral compound, you should have some chirality in the starting material. Either 1. Substrates, 2. Reagents, 3. Catalyst, 4. Solvents. Somewhere there should be some chiral environment to get a chiral product. This is a must. So any achiral starting material will give you a chiral product. Remember, it may be having a chiral carbon, but you will get always a racemic mixture. That is what you have to keep in your mind. So asymmetric synthesis, it tells you how to synthesize chiral compounds, directly without the requirement of separating the enantiomers. Preparation of chiral compounds directly. There are two basic ways by which you can synthesize. Two basic. I will just write one point here. Chiral environment, chiral starting materials leads to chiral products. This you should always remember. Now let us begin. One of the approaches, there are two basic ways. Number 1, 2 ways to synthesize. Number 1, you begin with a single enantiomer and do the reaction which will not affect the chiral atom. Begin with a single enantiomer and do reactions not on the chiral carbon. Don't disturb the chiral carbon. Don't do any reactions of that. If by chance, if you are doing that, there is every chance that it may get racemized. Okay, so this chiral carbon will direct or control the reaction on other sides. Okay, so begin with a single enantiomer and do the reactions which does not affect the stereo center. Which does not affect the stereo center. Number 2, what we are going to discuss, that is asymmetric synthesis or stereoselective synthesis. Or stereoselective synthesis. Okay, now, so let's look at the asymmetric synthesis. In asymmetric synthesis, I told you there are basically 4 methods by which you can achieve asymmetric synthesis. One is having an active substrate. Start with an active substrate. So I'll put active substrate. So if a new stereo center is generated in a molecule, which is already having a chiral center, you will have the chance of forming 2 diastereomers. We will explain this by taking a few examples. Let's look at a simple reaction. Reaction which are familiar to you. Let me take this molecule, pH. I have one chiral center here. Methyl group is chiral and ethyl. This is the molecule. Now let us do a reduction of this reduction. Using lithium aluminum hydride, LiAlH4. Let us do a reduction of this and see what will be the product. Now you will be knowing. Look at this. You have only one functional group. It's a keto group. So ketone on reduction will give you the alcohol. Yeah, that is known to you. Ketone will give you the alcohol. Now let's look at this one. If you look at this, you have the lithium aluminum hydride generates H minus. So H minus is the nucleophile. We know that. So this H minus can attack either from the front face. This is the front face which we are looking at. That's a front face. Now let us see whether that is a re face or psi face first. You must be knowing this, how to show whether it is re face or psi face. How do we designate the phases? You assign priorities to the different groups around the double bond. This is oxygen is having the highest priority, which is attached to this carbon. To this carbon, you have the ethyl group and this group, this whole group. So these are the three groups. One, this group is 2, and this is 3. So it is anti-clockwise. 1 to 2 to 3 is anti-clockwise. So this that phase, the side which we are at, where we are standing, it is the psi phase. It's anti-clockwise. The movement from 1 to 2 to 3 is anti-clockwise. So the attack, if the H is added from the front, this OH will be formed on the back side. If H is added from the front, OH will be formed on the back side. So this is the psi phase. So now let me remove all this. Yes. So this is the psi phase. The other side is, the back side is re phase. So psi phase and re phase. So this is the psi phase. Now when we are doing this, what will be the product obtained? What are the possible products obtained? Now, pH, you know, this will be remaining the same. You have to, this is 1 with the H on the side. And you have this. Plus, this is one possibility where the H is attacking from the back side and O is coming to the front. Okay, now you have the second product where you have, so these two are diastereomers. So as you know, this is a diastereotopic phase. This molecule is having a diastereotopic phase. Now the question is, which one will be the major product, which will be the minor product? Okay, in reality, what is obtained is, one of them is obtained in a larger as major product, the other is obtained in minor product. Now the question is, can we predict this? Is it possible to predict this? Yes. What we do is that there are two rules which we call as Cram's rule as well as the Felkin-Ahn model. Two rules. One is Cram's rule, the other is Felkin-Ahn. We will use Felkin-Ahn model here. To predict a product. Okay, so this is one reaction. We are doing that. Before doing that, I'll give you an interesting variation of this reaction. Look at this one. pH. I have another molecule which is very similar. You get the same product, but starting material is different. See here, see what I'm doing. So here is the aldehyde, not a ketone. Directly the aldehyde. Now if you want to get the same product, if you want to get the same product from this aldehyde, What you have to do, just think of it. What reaction you have to take? Just think and try to write by yourself. Yes, you require an addition of another nucleophile. Here it is not H minus, you should have ET minus. Tell me, what is the reagent to generate ET minus? Yes, MgBr plus. So if you react this with the ET MgBr, you will get the same products as above. Let me note right. You will get the same product. Again, the stereochemistry, how that reaction occurs, we have to check. We'll see that. Let me write a third reaction, something, a third variation of this. A third reaction, where I have a molecule with this, of course, it's not related to this, but have a look. The reaction is, here I have NBN2 and CHO. And this is the chiral carbon. Okay. So this is a secondary butyl group over here. And this is reacting with an enolate. This is nothing but your, what is this molecule? What is this? OMe, OLI. Yeah. Hey, can you just look at what is this? This is an enolate anion of which compound? Which compound? Think of it. It is CS3COOMe. You treat this, we convert this into the lithium enolate. React with methyl lithium. You'll get this compound. So this is the nucleophile. Okay, this is O minus Li plus. So this will act as a nucleophile. Okay. Now if this reacts, this nucleophile can attack again on this carbon. How does it happen? See here. This is how it attacks. And what product you get? Yes, you get a product. You have two possible products. OH COOMe, OH COOMe and NBU2, BN2. Now just note down, BN2 is nothing but benzyl. BN means two benzyl groups. That is, this is BN, CH2 group. Some of you must have forgotten that. Okay. So these are the three reactions which we have, and we have to see. Of course, you get the enantiomer, the other diastereomer also. That is, yes. Where do you have this NBU? Yes. CHO. So it is attacking here. Yeah. So already you have two chiral centers. So what we are doing is we have NBU OH here plus, see this, it may look a little complicated, we'll make it very simple to understand. NBN2 and see here, so this is the new chiral center which is generated, and COOMe. These are the two possible products. So these three reactions we will analyze today. Let's take the first reaction and see what happens. Yes, pH and now reacting with H minus. Now let us draw the Newman projection of this molecule. How does the Newman projection look like? For that purpose, what we do is we will keep the keto group up, and which group is down? Have a look. What group we have down? This is the group which is attached to the keto group. So we have on this side here this ethyl group here. Okay, we have the ethyl group. But now I will draw the three different groups. What you have to do is you take the largest one. This is the, see, you have three groups here. One is methyl, the other is H, and this is phenyl. The largest group is phenyl. So you can see here, and you hold the molecule in such a way that your phenyl group is perpendicular to this plane. The largest group, I'll write this large, is perpendicular to the plane plane of this ET and CO. So this is how I will draw. I will observe, take it. See here. This is the ethyl group. This is so black is ethyl. Black is ethyl. And then this is the keto group, and this is the second. So black is ethyl, and this is hydrogen. This is the methyl group. That is, this is a green one, green methyl group. I don't know whether you will be able to see this green color. I'm not very sure, but still, assume this is green. Now this is the phenyl ring. This is a phenyl ring, largest group. Okay. So now see, I should hold this molecule either this way. See, this is the keto group, this is the ethyl group. So this keto and ethyl is perpendicular to this, and at 90 degrees to this. This is the phenyl ring. So this is in this, this is a vertical plane. This plane is horizontal. So this is 90 degrees. So this is one conformation. Now if I draw like this, I will have my methyl group here and H here. So this is one way you can put it. The second one is this, you rotate this in such a way that it is just on the opposite side. This conformation is also possible. Okay, so we have this conformation is also possible, ethyl. See here, my pH, see, it is a back carbon. That's why we have kept this outside. So this is the phenyl group. And here is, now see on the top, what is there? You have hydrogen. And this is, yes, like this. See, this group is methyl group. So these are the two possible conformations in which, of course, you can have many. This is another conformation, this is a conformation, but none of them are stable. These two are the most stable conformation, reactive conformations. Now we have a nucleophile which should attack, H should attack this one. Let me make it H. Here is a nucleophile H minus. Assume this is H minus. So we are holding this in two different ways. Remember, the attack always occurs on this, in this angle. This is very specific. From the vertical, it should be 107 degrees, 107 to 108 degrees. There is a particular name for that angle. There is a particular name. I don't exactly remember. Dunitz-Budzi angle or something. Okay, forget about that. This is the angle on which this nucleophile attack on the keto. So it can be on this side or this side. From here or from here. Of course, in this conformation, it will attack only from this side. In this conformation. Because this side you have the largest penile ring. So, I have this conformation which I have drawn here. This is the second one. Okay. So, this should attack from here. My H minus should attack from here. Now, suppose I have this conformation. Now the Dunitz angle is this along this. See here. See here. This is the angle at which, see, this side is free. It cannot attack from here because of the penile ring. So this comes and attack here. Okay. Now compare these two. So that means I can draw on the other figure an attack from this side. Now itself you can understand in which side will be preferred. H minus attack here. H minus attacks here. This is preferred. Because this is the smallest group, this is a medium group. Here you have methyl group. See, this is methyl group. Methyl group is bulky. I should have made a big methyl group over here. A CH3 group itself. You can understand it will be really bulky. So, if I have this conformation, this one will be affected by the presence of this CH3. This is the CH3. Okay, so this attack is not feasible. So, this attack leads to minor product. This leads to major product. Now here comes the real task, how to convert this into the product. Okay, let us see how we can draw it. And see here. Yeah, if it is attacking from this side, no, it has to attack from this side. Yeah, this is the way it has to attack, right? See here, this is going to attack here. That means this double bond will break. This double bond of the oxygen will break. Let me try to break this. Yes, see here, it is broken. Okay, and see this double bond. So this one has reacted. See this. It will be forming this product. This is how it will look like. Okay. If it is attacking on this side, it will be opening to the other side. So this will be product obtained from this. Okay, then what you have to do is just rotate it and write the product. Let us write this. Let us write this. Now if I attack, see here, this will be bent to this side and H minus will be going. Okay, so how will it look like? And this will be bent to this side. See what I'll get. I will write the Me as such. Me, pH. See, no change for these groups. Now what I have is my H here, my OH here, and ethyl group here. Ethyl group. So this is what I have got. Now the task is to rotate this. Now we have to rotate this, the whole molecule, like this. See, it was originally like this. See here. Now what we have to do is we have to rotate this like this. This is a real task. You have to be careful. When I rotate this, I will get, see, this OH will be on the back side. I will have I'm just rotating like this. See here, I have my OH on the back side. H to the front and ET down. Okay, OH on back side, ET down, and ET I will just write, yes, ET, and then I'll have this group. See, I'm rotating like this. So my phenyl group will be over here. Okay, methyl group just rotating this way. So I have the phenyl group here, and methyl group will be pointing towards me. Methyl group will be pointing towards me. And this hydrogen will be down on the back side. So we will not write this. Yes. Okay. So this is the product. Remember, there is no change for the chirality of this. There will be no change for the chirality of this side. Okay. So this is a major product. What's a minor product? pH, H, ethyl, yes, methyl. This is a minor product. This is what we have predicted. This is what we have predicted as per this. Now what happened is, in reality, this product is in the ratio 3:1. This is 3 and this is 1. Now note one thing. All these minor and major products totally depends on reaction conditions. What the publication which is in this publication is giving you 3:1. Then they must improve this method by different techniques so that they give maximum amount of this. Industry will never have will never prefer to have such a combination. That you have to remember. Industry will never prefer to have such a combination. Because separation of this will be very difficult. So they must improve this process later, which we are not discussing. What are the conditions? They're all of course, trade secrets of the companies which are making such compounds. That you should remember. Anyway, in this experiment, they have got 3:1. Okay, now let us look at the second one. Let's. It looks to be very similar. See, we have H and ETMGBr. And you have the chance of getting two products, as you know. Let's see how this happens. Again, we draw the same fashion. Now it's easy to draw. Since we have drawn one of them, here this hydrogen, remember this. This group is hydrogen. On the ketone, it's an aldehyde group, not a ketone. Earlier we had ethyl. Now the other side is same. So we have two conformations like this, pH on this side. Okay. And yes. Yeah. pH on this side. Then we have, yes, same thing as before. And there is methyl over here. And it's H over here. That's right. Now what is, which is attacking species? So this is the way, this is the one which, this will be attacking from this side. I'll repeat the same thing over here. I'll repeat the same thing. With my phenyl group on the left side. I have the phenyl group here. I have the hydrogen here. Methyl here. H here and methyl here. So the angle of attack is this. That is, this angle should be approximately 107. So here the angle of attack should be this, because you have the phenyl ring. This side is occupied by the phenyl ring, will not attack. So this is where how it should have attack. So this will be the major. This will be the minor. Let's see what happens. Will you be getting the same product? Let's see. H, Me, and pH. And my ET is here. Remember, ET is attacking species. ET minus. Here, ET minus. So, ET is here. And this is my OH. And here is the H. So, this should be the major product. Now, let's just convert this into this. So, it is their equivalent. You rotate it. You get your phenyl here. Methyl. Yes. Phenyl here, methyl here. And your OH. Yeah, in this case, the OH is here. You have the ethyl. And you can see the OH is on the to the front. And your H is on the back side. Ethyl here. So this is the major product. This is the major product. Have a look on the previous one. Look at the previous one. You have the major product in which OH is on the back side. OH is on the back side, but here you have the major product OH on the front side. Plus pH. Yeah, should I write this second one? I think that's not required. Okay, I'll write it. Why? Because I just want to show the OH, H, and E. So this is the major product. This is a minor product. See how you can decide which product you want. How to prepare the product which you want. If you want this as a major product, you should go this route. You take this starting material, aldehyde starting material, ETMJ-VR reaction. Suppose you want this as a major product, go the other way around. Now this is obtained in 3:1. This is 3, this is 1. Opposite of what we had obtained in the previous case. Okay, same products, different. But remember, the mode of attack is just the same. Both attack occurs in the psi phase. Both attack is occurring on the psi phase. And that gives you two different products. So by manipulating the nature of the substrate, see, your substrate is chiral. Remember, this is chiral. It's a chiral reagent, a chiral molecule. So it is this group which is deciding the incoming group, where it is, in which direction it has to go. Now let us look at the third case. The third case is quite interesting. Like, see, let me. This is NBN2. And now we have the CHO group. It may look a little complicated for you to write the product, but still it's not very tough. So let me take I have this OME here and OLI here. So it is this Li plus. So this will go back. This will attack here. This will attack here. Again, what we do is here. Yes, this is the chiral center which decides. This is one group. This is the second group. And you have the hydrogen on the back side, on the front side. That is the third one. Now remember, in this case, you have NBN2 and this one. Which alkyl group or this, which is the largest group? That is what is the deciding factor. Now, experiment have decided, have given you the different experiments in which you have such substituents having an electronegative atom attached to the chiral carbon next to the keto group. These are considered as large group. that decides the stereochemistry of the final product, stereoselectivity of the final product. So this, see, attached, it can be NBr2, NBN, see, NR2, OR, any group like this, which is having an electronegative atom. These groups will be deciding, and this will be considered as a largest group. Okay, so we are drawing the, again, we have the hydrogen here. N, this is considered to be largest group. Okay, and then this group will be here. And H is here. See, you have the H here. This is H, this is methyl. Not methyl. This is, let it be. We are not interested. There is no need for, that will not be affected. Yes. So this is the H. This is the H which we are talking here. Okay. So same principle. It is the same principle. Only thing is, you are not considering this alkyl group as a bulky group. You are considering the electronegative atom, the group containing the electronegative atom, as a bulky group. Right. Now, let's do the reaction with this OMe OLi. How does it react? So this is one, okay, one conformation. The second conformation is this one, with the NBu, NBN on the other side. NBN2, NBN2, here is N dibenzyl group. Dibenzyl group. Okay, the dibenzyl group is this one, NCH2 C6H5 and CH2 C6H5. Remember, it's a protecting group like. Towards the end of the reaction, you are going to, this is the part of a synthesis of a drug, this particular reaction. So we have rotated the opposite side, where we get, this comes to the top. This comes to the top. This group comes to the top. Okay. And my hydrogen comes here. And I have the keto group here and H here. Okay, now attack. This is a one possible attack, which is not preferred because of the bulkiness of this. Look at this. But here, the attack is preferred from this side. So you get this as a major product. So what does it give you? This gives you, yes, yeah, I have the OH over here. Yes, this COOMe, and here I will have my H, and this, don't think it is complicated. You have, it's very, only thing is you have to just add the groups, that's all. Now we have the H here and H here, and here we have the NBu2, NBN2. Okay. Now, so this is the major product. And what is the minor product? And of course, we have to draw the, we have to straighten this, which is a really tough job. You should remember, the product is, yes, we will write the product here. Let me remove this. We'll write the product over here. The major product is this one, NBN2 with the OH to the front and COOMe. And this is CS3. So this is a major product. Okay. And remember, this is obtained in 20:1 ratio. See how the selectivity is increased. 20:1 means what they have claimed is it is 96:4 stereoselectivity. This is 96%, and the other one is 4%. So this is something like 4%. The other minor product is 4%, minor. That much of high selectivity, this should be a very great achievement, especially when it is having an industrial importance. So this is how you can predict the molecule, the product. Now the question is, why so much of high stereoselectivity when you have a electron withdrawing group like this, an electronegative atom attached to the next chiral atom? Why does this happen? The reasoning is a simple reasoning like this. See here, we have we can explain this on the basis of the orbital homo-LUMO interactions. We can explain this in a very simple homo-LUMO interaction. See here, we will just write N, the bond like this. See here, we have the NBN2. It is the NBN, that electronegative atom, that group, NBN2 is having a role in deciding the stereoselectivity. How does it happen? See here, this is the antibonding orbital of this bond, of that bond. Now this is the molecule. Let me draw the molecule as such. This is NBN. Then we have the, that double bond, attack of the double bond. So this is, let me draw this. Okay, so this is the CN sigma star orbital. This is the CN sigma star orbital, and this is the pi star orbital of the carbonyl group. Pi star orbital of the carbonyl. This is oxygen. Okay. Now, see here, the pi star orbital, I will shade this part and this part. It's a pi star of the carbonyl. Carbonyl is having a pi orbital, which we say like this. This is pi orbital bonding, with the electrons in the center. And antibonding orbital is opposite. That is why I have drawn it on separate side. Now this is the sigma star of your, say this. And here, this one is again sigma star. You know it is antibonding. So electron density, if it all is there, it can enter into this. So the interaction between these two. Now when this attacks, there is an interaction between these two. They are in phase with each other. So that leads to a situation where you have a clear-cut interaction here. See this. Oxygen and see this. They interact, and this is, I have this, yeah. So these two will be interacting. When they overlap with each other, this is antibonding orbitals. When they, so this will reduce. See, the antibonding orbital of the NBN sigma C and sigma bond, when it slightly overlaps here, the LUMO energy will be reduced. Energy of the LUMO. This is the LUMO. Which is the LUMO? Pi star orbital of the CO group is a LUMO. So, the pi star orbital of the CO group will have lower energy. See, for example, like this. It will have yes. This is yes. This is the CO. Yeah, CO LUMO. This is the NBN. So this interaction will lead to a further stabilization of the CO group by this much amount. So that will become the lowering of that results in the lowering of the LUMO, and that will enhance the reactivity. So always in such in addition reactions, high energy HOMO will react with a low energy LUMO. So whichever factor will decide will reduce the reactivity, the energy of the LUMO will be favoring the reaction. So this interaction lowers the LUMO energy of the carbonyl group, and that favors the final product. So that will lead to the final product to give you the correct. So addition to the CO nucleophile attack occur very easily now when this is happening. That is the reason why you have so much of high reactivity, high ratio of the product, 20%, and in the ratio of 20:1. So this can very easily decide. This rule can very easily decide which compound is the major stereomer. Now let me just give you some idea how to apply this Felkin-Ahn model. The three different steps which are required to apply this. First thing is step number 1, using Felkin-Ahn model. Okay, now this is very easy to apply. Probably this is more logically explained on the basis of your molecular orbital theory HOMO-LUMO interactions. So that is, and the other one, Kram's rule, also can be applied, but also that is just the small, medium and large group and attacking from that side. Okay, but that we'll take examples in next time and decide on that. Okay, now let us see how we can use this Felkin-Ahn model. There are three or four steps very clearly which you have to remember, which we have already done. I am just enumerating them. Step number 1, draw the Newman projection. Draw the Newman projection with larger group, with larger group, or electronegative group perpendicular to the CO bond, or electronegative group perpendicular to the CO bond, to the carbonyl bond. Okay, that's the first step. We have done this. The second, allow the nucleophile to attack. NU nucleophile to attack along the least hindered side at 108 degrees from the vertical, CO bond. This is the second step. Third, draw the Newman position of the product. And what is the fourth step? This is the most critical step, rotating the molecule. Okay, carefully flatten the molecule. Let me underline this. Carefully flatten the molecule. Flatten the Newman projection to form the normal structure, So these are the different steps which you have to follow to apply this Felkin-Ahn model. Okay, so this is about this. What is that? A Felkin-Ahn model. So this is the first way. So you have a substrate which is already optically active. Now you can have introduce a chirality into a molecule by following certain other steps. Number one, addition of a chiral group. Already there is no chirality. You can induce chirality by adding chiral group. So we'll take an example. Look at this one. This is asymmetric molecule, 3-pentanone. I take a chiral compound and attach to this, which is a chiral compound. Look at the chiral compound. Of course, these chiral compounds are generated from nature, which is the best source of chiral compounds in nature. Carbohydrates, proteins, amino acids, such molecules, simple glucose, fructose, sucrose, then L-amino acids. This can be isolated from protein from nature, either from plant source or animal source, whatever is that. They can be synthesized. Okay, cysteine is amino acid which can be obtained from human hair. It can be it's large amount. It is isolated. So such compounds are from natural sources. You can generate this molecule, and you can convert those natural products into other chiral molecules. So such a chiral molecule is generated from here. NH2 with OMe here and H here. Okay, so this is a chiral center. Now when you react these two, you can see the NH2 will form a double bond. NH2 will condense with this keto group and will form this molecule. This is the molecule. You have a double bond N with your OMe here, H here. Okay, so you got this. Now you treat this with the diisopropyl LDA, IPR N, IPR twice. Lithium diisopropylamide. First, it's a very strong base. Second, PRI. propyl iodide, NPRI, normal propyl iodide. Okay. So what happens is you replace this. So the product obtained is this one. This is yes, you get N, single bond N. Here is okay. So we have the N double bond N here. Methyl. Yes. Now you hydrolyze this. This part I am not wrong. N. So we have the OMe here and H. So the chirality is still there. So this molecule, yeah. Now you have introduced a group here. See this. You have, so what has happened is IPR will react over here. See this over here. On this proton will be abstracted by the LDA, and this will attack on this PR, and this will go off. So PR group will be, propyl group will be attached here on this carbon. This will be chiral, and this group will decide from which side it will attack. So the product will be optically active. Now you hydrolyze this with HCl, and you get this, this product. Okay. So this is the use of a chiral auxiliary. This is called a chiral auxiliary. Okay. Yeah. Okay. We'll stop at this point. We'll discuss the active reagents in the next class. Thank you.